Okay, hello everyone. So this is a recorded version of my presentation that I have done back in April 22nd. So the slides are exactly the same, the content are identical. I also try my best to capture all the Q&As towards the end of the slides. So yeah, just to start, my name is Amy, and I'm a fourth-year student at the University of Toronto studying biomedical engineering. I'm also a research associate at Harvard University working with Professor Joanna Eisenberg, but most importantly, I'm a volunteer at Hydrocephalus Canada, and I have been working with Ingrid and Shauna for the past 2 years because I want to bring my biomedical engineering background in hydrocephalus research to raise public awareness about this condition. So in the past 2 years, I have reached out to many Canadian organizations, healthcare professionals, and I've translated a few brochures from English to Mandarin and distributed to the Chinese-speaking community. So how I first started my research about VP Shunt was back in 2021, where I reached out and secured a summer internship at Harvard University working with Professor Joanna Eisenberg. At that time, the Eisenberg lab was successful in its novel material application on ear tubes. So I was hired to explore the potential of this material in other medical devices. As soon as I started my research, I reviewed a lot of literatures regarding to VP shunt, and I was shocked that the central technology for development of VP shunt has stagnated, completely stopped for over a decade, leaving patients with high rate of infection and device obstruction. So in fact, there are 120,000 Canadians who are affected by hydrocephalus, and around the world, this condition affects 1 in every 770 babies and 1 in every 200 seniors. And together, the condition also incur an over 2 billion medical-related charges. And the most common treatment for this condition is through the implementation of a VP shunt, which is over here. Hopefully you can see my mouse. But based on the literature that there's a 50% rate of failure within first 2 years of VP shunt placement. So really for me as a biomedical engineer, and as well as for the rest of the team, we know that we have to do something. Which brings us to my presentation today, which is an urgent solution to hydrocephalus and the story of what a small tube can do. So to start off my presentation, I want to simply acknowledge that humans' interest in brain can be traced back to a long time ago, that we can even see through this Leonardo da Vinci drawing back then in the 1485-ish, where we can already see a very detailed anatomical drawing of the brain structure, the skull, as well as the ventricle right here. And time flies by. The first recorded use of a perforated rubber tube as a shunt for cerebrospinal fluid drainage was happening back in 1903, which the shunt is over here. And of course, today we have much better VP shunt. And of course, this is due to this revolution in hydrocephalus treatment due to development of silicone rubber, which we still use it today, as well as the invention of implantable one-way valve. So this is what a VP shunt looks like. There is the tip part over here, and this part goes into the ventricles, and there are a lot of holes, you can see over here, that help the cerebrospinal fluid to drain. There are also the depth markers, so the surgeons know if the shunt has been placed in proper depths or not. There's the straight angle edge, which help the surgeons to insert the catheter straight. And for us, specifically for our presentation, we'll be focusing on the tip, just because based on our literature review, the tip is the most critical part of a shunt. And also based on our analysis of the current products, we noticed that majority of the shunt are the same, except their tips hole arrangement. And here, I just want to show a few current and most common VP shunt, which include big biomedical device company names such as Medtronic, Cook Integra, and Sofisa. Within these manufacturers, they all have a bit of different design in terms of material choice, hole arrangement, and in fact, our team have purchased all of the above shunt that I'm showing right here for our study. Even though there are many different designs for our VP shunt, the complication rate remained high, especially the problem of infection and obstruction. For the problem of infection, this has an incidence rate around 5 to 15%, which in the bottom image right here, we can see a VP shunt infection and migration in kid, causing swelling and redness as compared to the normal condition. Obstruction, on the other hand, contributed to more than half of VP shunt complications, and the problem of obstruction is difficult to tackle clinically and often result in revision surgeries. Therefore, our research question is that to what extent can we design a new VP shunt that reduces both the rate of infection and obstruction to minimize complication rate? And we have noticed that innovation has slowed down because there is a lack of rational approach to new solutions. Together with my team, we came up with this flange VP shunt design, which is now provisionally patented. And this VP shunt enables self-cleaning, and the geometrical manipulation and material choice ensures that there will be no bacterial colonization and no cell and macromolecule attachment, which together result in a decreased complication rate for patients. As compared to the standard of care catheter below, here's a zooming illustration. Our flange design will guide the flow to flush away the bacteria and cells, where a normal VP shunt will cause blockage and leads to clinical complications. Now moving to first part of our study, which is material choice. In our lab, we studied slip surface, which is a material infused with silicone oil developed by Professor Eisenberg. So our VP shunt consists of a silicone tube covering silicone oil, creating an extremely slippery surface that acts as a biofouling-free medical material. And as the name suggests, the surface is just too slippery for bacteria or cells to attach, making it a very promising material choice for medical applications. And for our bacteria study involving VP shunt research, we selected Staphylococcus epidermidis. I know this is a mouthful to say, so we'll just call it a skin bacteria because epidermidis means skin. So this skin bacteria actually contribute to more than 45 to 60% of catheter infections, and it is the major pathogen that causes shunt infection. So in the past, we have already validated the biofouling ability of slip surface in other medical device applications. So here we can see that taking a regular normal VP shunt that is available in the market, we can see that for the non-infused segment, there were a lot of bacteria, which can show in the purple stain. Where in the bottom image, in the middle one, which is the infused one, we see very minimal purple stain, which means minimal bacteria. And on the right-hand side panel, again, for the non-infused tube, we see a lot of bacteria, which this time is represented by the blue stain. Where compared to the bottom panel, when the material, the tube is being infused with slips, we see very minimal bacteria. And our slip surface also reduces brain cell attachment, which lead to less obstruction as compared to the other VP shunts that are currently available in the market. So here, our slips material column, we can see we don't see any cells, which means minimal cell attachment as compared to the other VP shunts, such as from Medtronic and Integra. And to further confirm our previous experimental findings, we also did microscopy images to visualize the commercially available BP shunt versus our slip surface. And the images I'm showing here are representative microscopy images for our slip surface. And on the Medtronic VP shunt, we observed many bacterial colonies forming on the surface, which are these white dots over here. However, on the right-hand side, the infused slip surface sample showed almost no bacterial colonies, which overall means that these images align with the experiments that performed previously and provided a strong evidence on how does the slip surface decrease bacterial adhesion. So I know I've been talking for 15 minutes, so I just want to take a quick break. I know I have been sharing just a lot of information that might be too much. So for a break, we'll do just like a fun fact regarding normal pressure hydrocephalus development history. So the story is about Dr. Salman Hakim, who is known as the godfather of normal pressure hydrocephalus. So how he discovered normal pressure hydrocephalus was that back then he had a 16-year-old patient in his home country, Colombia, where he noticed some very unusual symptoms compared to the other types of hydrocephalus. So he called Dr. Raymond Adams at Harvard to describe this new neurological condition. But back then, Dr. Adams kind of like dismissed him, saying that there's nothing new in the field of hydrocephalus. Everything has already been published. Perhaps you just don't have good libraries in Colombia. However, Hakim flew with his patient to Boston and performed a surgical procedure in front of Dr. Adams to convince him that there's indeed this new neurological condition, which kind of persuaded Dr. Adams that together they published some work and they called this new neurological condition, they name it as the normal pressure hydrocephalus. So after this journal publication, they all became friends. So we can see Dr. Salman Hakim on the right with co-author Dr. Raymond Adams on the left. So the moral of the story is that in the scientific field, a publication can heal everything. Okay, moving on to second part, which is the sign of self-cleaning shunt. So obstruction often occurs due to uneven flow distribution among VP shunt inlet holes. Typically, the majority of the flow occurs at the proximal ends, which is the end that is away from the tip, where minimal flow reaches the distal end, which is over here, that is closer to the tip. And this uneven distribution leads to blockages, primarily at the proximal end, which is shown over here. That blockage happens at the proximal end. And this is really bad because once the proximal end is occluded, the entire VP shunt does not work anymore, even though the distal inlet remain unobstructed. And clinical cases further support this because we have seen a lot of clinical images of the explanted VP shunt that we see this consistent blockage happening at the proximal end. So just to test out this argument that majority of the flow enters from the proximal holes, we did this ink flow study. So what happened, what I will show in the video is that you will see a drop of ink will be added to the water reservoir, and this reservoir is mimicking the brain ventricle. And obviously this camera is set up to record everything. And I just want everyone to pay attention to the proximal holes, which is labeled in the red dot. So you can actually observe how the majority of flow is actually going through the red dot. So that was the video. I also have some screenshots here just to again show you majority of flow is indeed entering from the proximal hole. And we also did a computer simulation, which is on top over here to confirm that more than 80% of the flow actually enters from the proximal holes, which is hole number 4. And how we came up with this flange design is that back then we have multiple candidate designs, each with different flange distribution. Some have like straight flanges, some have curved flanges. And then we ran the design in computer simulation, and we picked the design that has the highest shear force on the flanges, which is the part over here, which can help us to flush away the bacteria, and therefore we call it self-cleaning. So my team and I, we have been just actively pushing forward this project. And some of the ongoing effort that we are doing is that first manufacturing our VP shunt. So we started from something very beginning, trying to create a lumen and then add the inlet holes, flanges. And very soon, I believe we'll be able to have our first prototype of our self-cleaning flange VP shunt. And also we are working on a preclinical trial using mice to study the safety of our material. So here, this is the trial implant test. So what we do is that we implanted a tiny piece of our slips surface into mice's brain ventricle and to observe the safety of the material. And here's a recap of my presentation. So we came up with this flange ventricle design, which is now patented, that enables self-cleaning. And flanges, the slips material ensures that there will be no bacterial biofilm formation and no cell and macromolecule attachment that result in a decreased complication rate for patients. As compared to the standard of care VP shunt below, this is the zooming illustration. Our flange design will guide the flow to flush away the bacteria and cells, where a conventional VP shunt would cause blockage and leads to clinical complications. Here are the Q&As that we covered back then in our live discussion. So the first question was that how does this new shunt help with scar tissue? So even though we haven't done the specific testing towards scar tissue, but from a biomedical engineering perspective, scar tissue are often resulted from inflammation, and inflammation and infection are also related, and they're related. So if our slip material can help with infection, what we hypothesize that we anticipate the slips material will also help decreasing the chance of inflammation and therefore decreasing the chance of scar tissue formation. The second question is that have you done any longitudinal study yet? And by longitudinal, the audience means 1 month or 2 months, things like that. So the short answer is not yet. For my study, the study duration is 1 week. And for the cell studies, the duration is usually 24 hours. But this is definitely a great proposal, and we definitely look forward to do a longitudinal study later in our research phase. Another question is that is slips material toxic? This is actually an excellent question, and our top priority obviously is to make sure that our device is safe for the patient. So slips material is not toxic. So how we know is that first, we have done cell studies which going back just to the slide. So in addition to testing this brain cell attachment, we have done a preliminary safety testing just to confirm that SLIPS material is not toxic to the brain cells. And also, since we are based on our animal trial, I'm just trying to find the animal trial slides, which is over here. So the animal trial was done just to confirm the safety of the material, and no, SLIPS is not toxic. Another question is that does this new shunt contain any latex, given that many people are allergic to latex? No, our material does not contain any latex. Our VP shunt is made of silicone, with silicone, the same material as many of the other conventional VP shunt. How did you come up with the flange design? And so just going back to my slide, which is over here, how we came up with this design style. First of all, we have multiple designs. So we have many different candidate designs, and we screen these designs based on this parameter, which is shear force. And eventually for example, out of the 5 designs that I'm showing right here, we found that design number 5 has the highest shear force along the flanges, which compared to design number 1, design 5 actually improved the shear force by more than 10 times. And the question is that what is shear force? So I have an image over here, and shear force is a force acting in a direction that is parallel to a surface or cross-section of a body. How does this new shunt affect the electronic valves or the electronic component in the VP shunt? So since we are only modifying the tip of the VP shunt, and the electronics are often included in the valve, we don't believe that our new VP shunt will interfere with the electronic valve in any way. So we anticipate that there will be no negative impact, no negative influence with the electronic valve. And the question is that does the SLIPS only cover the external surface of the shunt? No, since we are infusing our VP shunt into silicone oil, so both the inside and outside of our VP shunt will be covered with the SLIPS material. Okay, so I just want to thank all my collaborators, institutions, and funds that supported this work. I'm very fortunate to be able to work in such a multidisciplinary team, and thank you so much once again. Thank you once again to Ingrid, Jeff, and Melody for having me to do both the live discussion as well as for this recorded section. And thank you so much for listening. If you have any additional questions, feel free to reach out to me, and thank you once again.